Okay, so this is going to be our final video dealing with max power transfer. That doesn't mean we're not going to talk about max power transfer later in this course or in other courses. It's just we will have learned enough that we will be able to have those discussions here. So the objectives here, what we've learned in the previous videos, is that in order to get max power transfer, we need to set the load to be the equivalent resistance of the circuit. Now, let me emphasize here first, we are only considering circuits with independent power supplies. And I'll put it in here red. Finding REQ for dependent power supplies requires more work. So what we're going to be talking about in this video does not allow us to find REQ if an independent power supply is present in the circuit. It only allows us to find REQ for circuits that have independent power supplies. Now again, your text probably has a discussion on how to do the dependent power supply, so I'd encourage you to read that. I look at it, it's always good to gain additional knowledge, even if you're not going to be tested on it, because you never know when that knowledge could be useful to you. But we will only be considering in this course circuits with independent power supplies. Alright, so how do we find REQ? Well, the first objective here is we first turn off all independent power supplies. Now this is extremely important here. Voltage sources become shorts, wires. Current sources become open circuits. And you can think about this just briefly on why this justification makes sense here. If you're turning off a voltage source, so there's 0 volts, well, what's a circuit element that has 0 volts dropping across it? Well, you might say, well, it's connected to ground. Yeah, but I'm not thinking necessarily, okay, it's connected to ground. I'm trying to think of a circuit element. And there's no real, the circuit element isn't really necessarily a circuit element. It's a wire. Wires, you know, from a theoretical standpoint, we say, oh, the voltage drop across a wire is 0. Now, in practice, that's not true. And when you're talking about the power industry, like voltage transmission lines and everything like that, the voltage drop across power lines can actually be critical to know what it is, even though they're just, quote, wires. But, you know, for our small circuit diagrams we draw, those wires are considered shorts and there's 0 volts across them. And then current sources become open circuits. And if we think again about, well, why would we have it be an open circuit? Well, we don't want any current to be flowing. Well, we know if we have an open circuit, no current can flow through it. So that's how I can set the current source to be 0 amps. Open circuit. So let's look at a circuit here. Oh, well, that's the first thing. I should tell you the second thing here. Second, find REQ. And then the third, set REQ to our load. So let's look at an example of this, a very basic one to start with here. So let's look at this circuit here. So I'm going to have a voltage supply here with a resistor, and I will call this here 1 kilo ohm, and then we'll have 2 kilo ohm here, and let's say 3 kilo ohm here. And then I'll draw it with red here. What we're trying to do is we're trying to attach a load here for max power transfer. So what should RL be? And I'll go ahead and say that this is, it doesn't matter, I'll say this is 12 volts. And so I want to find then what RL should be. Well, the first thing, we turn off the power supply. So by turning it off, I'm going to just erase this, because we said a voltage source becomes a short circuit or it becomes a wire. So that's what I have now. I turned off my voltage source. So voltage source off. Now, the reason I've left the RL there is this is where people make mistakes here when they're looking at what the RL should be here. Most common mistake I see on this is that people say that the load resistance here should be 6 kilo ohms for max power transfer, because they're saying, well, the 1, 2, and 3K are in series. They're clearly not in series if we draw it like this. And I'm going to redraw it even one more time here, where I'm going to move this 1 kilo ohm off to the side here, and then I have this 2 kilo ohm and 3 kilo ohm, one kilo ohm, and then of course we have attached my load resistor. But because there's these wires here still, what we're looking at is we're looking for the equivalent resistance looking in this way. You know, what is the load seeing as far as an equivalent resistance? And it's seeing, well, this 2 and 3K are in series. The 2K and 3K are in series. But that combination is in parallel with the 1K. Because again, if we just think about it here, clearly the 2 and 3 are in series. Hopefully we all agree with that. So if I do the 2 and 3 in series, of course we get 5K for that. So you'd have 1K here, and then 5K here. And then again here, this is being attached to a load. So clearly, just from this picture, this 1K and 5K are in parallel. And so that's what my REQ would be. So REQ is going to be 1 over 1K plus 1 over 5K. Inverse, I don't know why I did that as opposed to the other method. Because if you do that, you get that this is approximately 833 ohms. Which, of course, if you did the multiplication, it's just 5 divided by 6, or 5k divided by 6k, which is 5 kilo ohms squared, technically divided by 6 kilo ohms, which gets you 833 ohms. So then that means for max power transfer, RL is going to equal 833 ohms. So I said that this was going to be the last video relating to max power transfer, and I lied here because I'm going to do one more with one more example here. But what I'm going to first do before we do that here, I will say though that often you don't get to pick RL you have to design your circuit for RL. And what do I mean by that here? Well, I'm going to finish this video with this quick kind of example here. So I've got some circuit here. And Req of this circuit is 1 kilo ohm. And I want to attach this to an 8 ohm speaker. Well, I'm definitely not going to get max power transfer here. In fact, you connect it up here, you might not even hear anything from the speaker because you're not getting very much power to the speaker at all. All of the power is still getting dropped across in the circuit. None of it's actually reaching the 8 ohm resistor. So I'd have to modify the circuit diagram. Now there are plenty of ways to do this. This is just like the most basic way to do it. It's not necessarily what I'm claiming is this is the best way to do it. It's the most basic way. Is that currently this circuit has an equivalent resistance of 1K. Well, maybe what you can do is instead of if you want 8 ohms here, well, what you'll do is you'll put another resistor here, R, and you'll put it in parallel here because it's now going to be in parallel with that 1K. And if I think about it here, well, 1K is very big compared to 8 ohms. If I set this at 8 ohms, so if I set that R at 8 ohms there, the new Req is 1K in parallel with 8 ohms, which would be 8 times 1,000 divided by 1,008. Which if you do that, you get 7.94 ohms for the new Req, which is now really close, within tolerance, quite frankly, of the 8 ohm speaker. So that's a trick, and when they're talking about matching impedances, that's what they're referring to, is that you have to make sure to match impedance because you want maximum power transfer. Now I said it's not the only way, and it's not necessarily the best way to do it, but it is a quick, way to just drop your impedance of a circuit. Is if you've got a circuit with an equivalent resistance and you need to drop that output impedance, put a resistor in parallel with it and it will drop the output impedance. Now as I said, it's not necessarily going to be the best way because resistors tend to generate a lot of noise and things of that nature, but there are other ways to then deal with that noise using capacitors and stuff.